Well, here's one more example on Bernoulli theorem. So we have this tall building, and this tall building, it has a height of 50 meters. And there's a water pump right here, and this water pump is pumping water. Well, it's a water pump, so it will pump water only. Let's try to make a straight line. There's a water, there's an aluminium or metallic water tube, a water pipe, and this water pipe, this is a water pipe which has same cross section throughout, so it is, the area of the pipe does not change with length. And this water pipe, I am not able to make it very precise, but let's assume the area does not change of this water pipe, and the water which is being pumped up with a velocity of 0.1 meters per second. This is how the water is coming out from the other end of the pipe. And the density of water is given to be 1000 kilogram per meter cube. So the question is, how much pressure pump is supplying? So that there is some pressure which is being supplied by the pump, and how much is the power of the pump? How much power pump is putting in moving water from the bottom to the top? So let's see. So let's write, and also we know that atmospheric pressure is P naught here, or let's, for the sake of simplicity, let's say there is no atmosphere. There's no atmosphere. It won't really change anything. So let's say there's no atmosphere. Okay. So how much pressure pump is supplying? Let's say it's supplying pressure P plus, according to Bernoulli's theorem, half rho V square, and this is V, plus rho G H is 0, and this should be equal to, at the top, let's say pressure is, well, you see, for the sake of, let's keep it realistic. Let's say there is atmosphere. So pressure is P naught equals 10 power 5 Pascal. Why do ignore that? 10. So at the other end, we know pressure will be just atmospheric. There is no pressure than atmospheric. So water is coming out with no atmosphere. It's barely making to the top. That's the point. It's barely making to the top with no pressure. So it's 10 power 5. Okay. Plus half rho V square stays the same, plus rho G multiplied by H, which is 50. Okay. So P turns out to be, this gets cancelled anyway, and we get 10 power 5 plus rho is 1000, G is 10, and H is 50. So that gives us 10 power 5 multiplied by 5 multiplied by 10 power 5, which is nothing but 6 into 10 power 5 pascals. I hope this is clear why it's just P naught at the top. So if water is barely making to the top, that's what it is doing, then the pressure of the water is 0. If it had more pressure, it might have gone even up. But let's say it's not really able to climb more than 50 meters. The best it can do is 50 meters, so it runs out of pressure. We need pressure to pump water upwards. So let's say right here it runs out of pressure. So all that remains is just the atmospheric pressure. So that's what it is. Okay, so this is the pressure. But how much is the work done by or how much is the power of the pump? Or where power by power means work done every second. That's how power is defined. How much is the power? Well, what should we do? Now, physics does not mean we blindly follow formulas and get the answer. We use Bernoulli theorem to find the pressure, but does not mean we are going to use Bernoulli theorem again to find the power. So let's use our intelligence. What is this pump really doing anyway? What it's doing is it's taking some amount of water here. It's taking some amount of water here and it's pumping it to the top. So it's all the work which it's doing is actually going in changing the potential energy of the water by lifting it from here to the top. So every second, how much is the volume of water which is being pumped by the pump? So every second, volume of water is going to be velocity of water times the area of cross section. I should have given the area, I'm sorry. Area is also given to be 0.01 meters squared. That is the area of the pipe. That should be given. Okay, times rho is nothing but mass of water coming out. Well, not coming out, actually water pumped up. You see, water is moving like this. So here, every second, water is traveling velocity because it's traveling with speed v. This is the volume of water which enters the pipe every second. V amount of water, V length of water enters every second with a cross section A. So AV is the volume of water, and when you multiply the volume by density, that gives the mass of the water pumped up. So this is the mass of water pumped up every second, because V is the length of water being pumped in the pipe every second. So mass of water pumped up every second. How much is the change in potential energy of this water? It's V A rho G H. So GH, mgh, we know mgh is the change in potential energy. So this is the change in potential energy of the water every second, and this is what? V is the velocity, 0.1, A is the cross section, 0.01, rho is the density, 1000, G is the gravity, let's take it to be 10, and H is the height, which is 50, and that gives us 500 watts. Well, this is mg, units for energy. Why watts? Because this is actually energy per second, because this is being done every second. So 500 watts is the power of the pump. This is around 7.7 horsepower. The power of motors or mechanical motors is usually measured in horsepower. A horsepower is close to 750 watts. Close to 750 watts. Anyway, so the way we calculated was that we calculate the amount of water which is being pumped in here, and then we know the whole water is being pumped upward from here to here, and this is nothing but change in potential energy, and that's what we calculated. And because this is happening every second, we know that this is the amount of work motor is doing every second, and that's why it's the power of the motor.